Hello everyone, today we're going to look at the derivative. We know the slope of a line is given by m equals y2 minus y1 over x2 minus x1. And as I've said before, sometimes this is denoted by this triangle y divided by triangle x. Remember that triangle is the Greek capital letter delta, and it means a small change in. So a small change in y divided by a small change in x. But what we're going to look at is, what if we don't have a line? What if we have a curve? So what we do is we let P be the point of interest on the curve, and we let Q be another point on the curve, say x2, y2. And then the line connecting these 2 points is called a secant line. So for example, if I had some curve and I had Q over here and P over here, and I wanted to draw a line between them, this line in blue is called a secant line. And what we're going to be interested in is having our P move actually closer to Q. So I'll have another P here, and I'll draw another secant line. And then I'll have a P even closer, and I'll draw another secant line. So I keep moving P closer and closer to Q and drawing these secant lines. And what we're interested in is the limit of these lines as Q goes to P. This new line is called the tangent line. So here's a nice picture of it. So again, the blue line is the tangent line. The secant line. The blue line is the secant line because it's connecting P and Q. And then as Q gets closer and closer and closer to P, we get closer and closer to this red line, which is the tangent line. So what we're doing is we're taking a limit. So we're going to see the math behind this picture. And what we're really interested in is not the line so much as the slope of the line. We want the slope of the curve, and the slope of the curve is the slope of the tangent line. So I'm going to let P be the point x comma f of x. Remember that y is f of x. So this is just another word for y. Q we're going to call x plus h comma f of x plus h. So this is my x2 and this is my y2. I'm moving a little bit over from x. So x plus 0.01, x plus 0.005. Somewhere close to x, but not quite there. And then f of x plus h is just a corresponding y. So we want to look at the slope between these 2 points. So I plug it in, and then I notice that x plus h minus, that should be an x. X plus h minus x is h. So again, that should be an x. And then again, what we're interested in is the limit of this function as q goes to p, and that is the same thing as h going to 0. As h goes to 0, q goes to p. So this is the big thing that we're going to look at in this section. The limit as h goes to 0 of f of x plus h minus f of x all over h. And this is coming directly from the definition of slope. So remember before when we were doing function notation, I said you're going to see f of x plus h a lot. And this is exactly why. It's in the definition of the slope of the tangent line. The slope of the tangent line is called the derivative of y with respect to x. So the derivative of your function, y or f of x, it could be the derivative of f, depending on which one you want to call it, with respect to x. It's really going to matter what your variable is in this case. We're going to see it come up later on in the course. So you want to get used to doing it now. It's the derivative of y with respect to x. X is your independent variable. Y is the dependent variable. It's also sometimes called the instantaneous rate of change. The slope is a derivative, is a fraction, which is a rate, if you remember from previous math courses. So every time you have a fraction, you can think of it as a rate. It's a rate of change. And if x is t, then you can think of it as how fast something is changing. To find the derivative is called differentiation, or you differentiate a function to find the derivative. Do not use the word derive. Derive means taking things and creating something new from it. So derive and derivative are not the same thing. Some notation for the derivative, we can call it y prime. We can call it f prime. So this is y prime. So this accent or this apostrophe is prime. Y prime, f prime, or dy dx. So this is just dy dx when you say it, but it is dy over dx. This is Leibniz notation right here. It's one of the mathematicians that kind of created quote-unquote calculus. And that comes directly from that delta y, delta x. Delta starts with d, so that's why it's a d. And remember, that just means a small change in. And we're going to see Leibniz notation come up again later on. It's going to be really important. You want to use that versus y prime sometimes. So just remember that these three things all mean the same thing. It means the derivative of y with respect to x. So we're going to do some examples. Differentiate f of x equals x squared plus 2. So we're going to need to know what f of x plus h is. So go back to function notation. Everywhere I see an x, I'm going to plug in x plus h. So this becomes x plus h squared plus 2. Remember, when you're squaring a binomial, you need to FOIL it. So it's x squared plus 2xh plus h squared. Don't forget about the middle, the o and the I from FOIL. And then plus 2. We can't simplify this any further. So now we're going to plug it into the fractional part. We haven't talked about the limit yet. So this is just the f of x plus h minus f of x all over h. So here is my f of x plus h. Here is my f of x. It's just the x squared plus 2. Remember, you're subtracting that entire thing, so don't forget to distribute your negatives. The x plus 8, the x squareds cancel, the 2's cancel, and you're left with 2xh plus h squared over h. We are only going to be concerned with derivatives of polynomials or things that are like polynomials, x to a power. And in this case, when we're doing the definition here, everything that's in f of x is going to cancel with something in f of x plus h. And you're always going to be left with terms that have an h in them. If you do not, if you have a 2x or a 5 or a 3x squared, then something happened. You will always, always, always have only terms with h's left once you've subtracted f of x. So this is a good place to stop and think, did I do it correctly? So if everything has an h, you're good to go. And the reason we want that is because we're dividing by h. And the goal here is to get rid of the h. If every term has an h, I can divide by it, and I'm left with 2x plus h. If every term didn't have an h in it, I couldn't divide by it, and I couldn't get rid of the problem where if I plugged in h was 0, I would get something undefined. So remember, I'm concerned with the limit as h goes to 0 of this guy. So what is the limit as h goes to 0 of 2x plus h? Well, this is a polynomial. It's continuous. I can plug in h equals 0. And if h is 0, I get 2x. So let's try another one. Find the derivative of 3x squared plus x. So again, we need f of x plus h. So that's 3 times x plus h squared plus x plus h. Don't forget that this x also becomes x plus h. If I do it out, I square out my x plus h, I multiply everything by 3, I get 3x squared plus 6xh plus 3h squared plus x plus h. Then I'm going to plug it into that fractional part that we have. Don't forget, again, to distribute the negative. My 3x squareds will cancel. My x will cancel. So again, everything from my f of x, everything from this part cancels. Everything that I'm left with has an h in it. Because everything has an h, I can divide by the h. Don't forget that h divided by h is 1. It doesn't cancel to a 0, it cancels as a 1. And then again, we're interested in what happens as h goes to 0. Again, it's a polynomial, it's continuous. I can plug in h is 0, and I get 6x plus 1. So we're going to see this x plus h squared a lot in these coming sections because there's not much else we can do with it. We will have one where it's cubed, but as soon as we get to the 4th or to the 5th, it gets really messy and really long. So the most we're going to see is x cubed, but mostly we'll see x squared. So get used to squaring x plus h. As another one, we have f of x equals pi minus 4x squared. And here I want to find y prime or f prime of 2. So again, this will be the same thing as f prime of 2. I want to find the derivative when x is 2. In order to find that, I need to first find f prime of x. So you plug in your 2 at the end. So f of x plus h is pi minus 4 times x plus h squared. Again, don't forget to distribute the negative. You're subtracting that entire thing. And then I'm going to plug it into the formula. The pi's cancel. The 4x squareds cancel. And I'm left with negative 8xh minus 4h squared all over h. Again, every term has an h, so I can divide by it. Negative 8x minus 4h. I'm interested in what happens when h goes to 0, so I get negative 8x. So this is y prime, or f prime of x. If I want f prime or y prime of 2, I just plug in that x is, that should be positive 2. I think I changed it halfway through it. And I get negative 16. So y prime of 2 is negative 16. If I wanted y prime of negative 2, then I would get what I had written, which is 16. Okay, and we'll do one more example. So if y equals x cubed, find dy dx. So again, I'm trying to introduce the different notations for the derivative. I had f prime, I had y prime, and now dy dx. So f of x plus h is x plus h cubed. And if you want to cube it out, you can do x plus h squared and then multiply that by trinomial by x plus h, distribute all of it. If you know Pascal's triangle and you know the shortcut, it will be a lot easier. If you don't know what Pascal's triangle is, you can either Google it or you can ask me about it in next class. But whatever way you do it, you should get, once everything is simplified, x cubed plus 3x squared h plus 3x h squared plus h cubed. So you're going to have 4 terms. You're going to have an x cubed, an x squared, an x, and then some term with no x. I'm going to plug it into the formula. So I'm going to subtract x cubed. Those two guys cancel. Everything else has an h in it. So I can divide by my h, and I get 3x squared plus 3xh plus h squared. Again, I'm interested in what happens as h goes to 0. Again, it's a polynomial, it's continuous. I can plug in h is 0, and I get out 3x squared. We're not always going to have to do this limit definition. We will talk about shortcuts later on, but for now we have to make sure we're doing the full limit definition, which again is why I'm not going to do things like x to the 4th or the square root of x or x to the 2/3 yet. We'll do those more complicated ones later once we know the nice shortcut for it. But read through the section, try out the homework, and let me know if you have any questions. Good luck.